In this video, we're going to look at an equilibrium involving PCl5 and its decomposition into PCl3 and chlorine gas, and examine how this equilibrium depends on pressure. You may remember learning about this in general chemistry, that pressure also affects, for gas phase reactions at least, the equilibrium. In general, as we increase the pressure, our system will tend towards the side of our reaction that has fewer moles of gas. And that is not a change to the equilibrium constant. It is instead, it's an example of the Chatelier's principle. But let's look at this quantitatively instead of qualitatively. So we have this reaction, PCl5 goes to PCl3 and Cl2. And let's go ahead and write out what is Kp for this reaction. It's pretty straightforward. We have the partial pressure of PCl3 times the partial pressure of Cl2, our products, divided by the partial pressure of PCl5, our reactant on the bottom. Now let's imagine a specific situation where we have 1 mole of PCl5 to start with. So that is our initial condition. And let's see what happens. And we can think about this in terms of the extent of reaction. We're actually going to use this variable that we've defined prior to this. And think about what is Kp as a function of psi. Okay, so first let's think about how can we define all these partial pressures in terms of psi. So let's remember. So our moles of PCl5 will have our initial moles, 1 mole, minus our stoichiometric coefficient, which is 1, times xi. And this just comes from, again, the definition that we have for extent of reaction. The number of moles of Cl2 and the number of moles of PCl3 are both just going to be equal to positive xi because we have no initial moles of either of those. So these are just based on the definitions. Now, what we need to do is then remember that we need to keep track of our total number of moles because we're going to be producing additional gas molecules as the PCl5 dissociates. All right, so N total is going to be equal to our 1 minus xi plus xi plus xi, right? So this is our PCl5, and this is our Cl2 and PCl3. So overall, we'll get a net of 1 plus xi moles in total. Okay. So now we need to use those values of moles to get partial pressures, right? We know that our partial pressure is going to be equal to our total pressure, right? So P, for example, P for PCl5 is going to be equal to our total pressure times the mole fraction of PCl5. Okay, and our mole fraction of PCl5 is how many moles of PCl5 do we have divided by the total moles. So we'll end up with P times 1 minus xi divided by 1 plus xi. Right, that's just based on our definitions here. Okay, and we can write out similar expressions for our Cl2 and PCl3. These are going to end up being the same. For Cl2, we're going to have P times xi over 1 plus xi. And that'll be the same for PCl3 because they're being produced at the same time, right? If you produce a mole Cl2, you produce a mole PCl3. Now we can go ahead and plug these into our Kp expression, right? So remember we have our products, so we'll have a P times xi over 1 plus xi. We'll have 2 of those. One for our Cl2, one for our PCl3. And in our denominator, we'll have PCl5, which is P times 1 minus xi over 1 plus xi. All right. Now let's go ahead and simplify this a little bit. Well, one of our total pressures is going to cancel here. We'll have a xi squared on the top and a 1. We can cancel. All right. Let me not try and cancel too many things to start with. We'll have a p times xi squared in the top divided by 1 plus xi squared. All right, so that's these terms down here, and multiplied by 1 plus xi over 1 minus xi. That's just taking our denominator and reversing that fraction, so dividing by that fraction so everything swaps. So this squared will cancel here, and we'll end up with a xi squared over 1 plus xi times 1 minus xi is equal to 1 plus xi squared. Sorry, no, 1 minus xi squared. Times the pressure. And one thing I need to emphasize here is that this is xi at equilibrium. So what is our extent of reaction at equilibrium? Okay, and so now we see that the equilibrium constant and has a pressure dependence. So this shows that mathematically, we can plug this in quantitatively and get an expression here where we get a value of Kp, and that value of Kp has a pressure dependence. This is a mathematical illustration of Le Chatelier's principle for this particular reaction. That if we change the pressure, not the equilibrium constant itself, but the partial pressures of our gases are going to shift, xi will change. Kp is a constant. I just need to reemphasize that. This is a point that's emphasized in the book. Kp does not depend on pressure. Kp is a constant. But for the equilibrium, to maintain that equilibrium constant, if the pressure changes, the relative amounts of our PCl5 and PCl3 and Cl2 have to change to keep that Kp at a constant value. All right, we'll go ahead and pause here, and in the next video we'll look at consequences of this and how we can actually understand what's going on with this reaction.